Hello. So today we're going to talk about chemical kinetics. It's chapter 15. So in order to talk about kinetics, which is how chemicals are going to react with each other and the rate of those reactions, we need to talk about what we need in order for a chemical reaction to technically take place. And so the basis of that is called collision theory. So once the molecules collide, they can react or not, and that's depending on two main things. One, does the collision have enough energy to break the bonds that are holding the molecules together, right? Because that's a chemical reaction. You have to have bonds break, okay? Otherwise, you have a mixture. And the second point is whether the reacting molecules collide with the proper orientation to facilitate new bonds to form. So here's our first point, the effect of collisions. And so we have kinetic energy, right? The energy of movement. And so that's looking at two different molecules that we want to have a chemical reaction. And so are they just colliding with a little bit of energy and then they both kind of go off in their own way? Or do we have massive chemical reactions where these atoms are forced together, forcing those chemical reactions to break and then reform? Okay, we have the orientation effect as the other considered factor. And so what that is let's say we have a molecule like this one, and in order for it to react with this molecule, it has to hit in a certain way. So let's say that if these are three-dimensional in space, and so they can move freely, and let's just say these two molecules come into contact, and they come into contact in this formation. So they're just touching on the ends, okay? But let's say for these two chemicals, that will not result in a chemical reaction hitting in this direction. So even though they're mixed together in the same container and allowed to interact with each other, if these two molecules do not hit the correct orientation, they will not react. Let's say we have this molecule up on its side, and this is floating around in the container, and so is our second molecule. Now let's say the second molecule comes into this little opening and is able to hit that middle carbon, and that is what is needed to have a reaction between these two chemicals. Then they have to hit in that exact same point. Okay, so we would have a reaction here, bonds would break and reform, we'd get two new products. But if we had two molecules hit in any other orientation, there's going to be no reaction. That's what the orientation effect is discussing. All right, but kinetics is about rate. So not only do we have criteria for the reaction to take place, but we're going to look at the main focus in this chapter is how our reactants and products are being used up and made. And so we have a definition for reaction rate. So it's measured in terms of how much the concentration decreases, if we're talking about reactants, or how much the product concentration is going to increase in a given period of time. So we have a reaction down here of hydrogen, iodine, and the production of HI gas. We get two molecules. So if we're looking at just the rate of hydrogen breaking down, decreasing concentration of our hydrogen reactant, there's a note here that we use a negative sign in front. Why do you think that is? Well, it's because it's a reactant, and so it's going to decrease as time goes on. We're making a product. And so with this reaction, looking at the reactant losing concentration, we're decreasing it. That's why we have a negative sign in front. If we were talking about the formation of a product and its rate, we would not have that negative sign. And then what else is here for our rate equation? We have a change in on the numerator and denominator. Okay, these brackets that you see around the hydrogen written here, that means concentration. So instead of writing 1m, capital M for molar, we draw these brackets. It's just a little quicker to write, and it's the form for kinetics. So that's what this means, the change in the concentration of, in this case, hydrogen, divided by the change in time that we want to look at. And so we would rewrite this now. If we extrapolate the change, we could say that we have hydrogen at time 2, our T final, minus the hydrogen concentration at T1, whatever our starting time is, and then, excuse me, the difference in the times as well, time 2 minus time 1. Okay, and so that is our rate at one moment. We can also look at an average rate. That's measured concentrations in any particular time period. And so when we get an average, we're taking what's called in math the linear approximation of a curve. And we could say that the time interval, the larger it is, the more the average rate is going to be different from the instantaneous rate, because we're broadening our area that we're looking at. And so let's take a look at instantaneous rate. Now, if you've taken calculus, lucky you, but we're going to just briefly talk about the application of a calculus derivative and kinetics. So if you've had calculus, you may recognize what's on the screen there in the bottom right corner. I've just grabbed a picture explaining what a derivative is. And a derivative we would take is just a spot on a line. We have f of x function being graphed there in blue. And so we just mark anywhere on that function a point we want to study. And if we take the derivative, that's taking a tangent at that point. So it's at that instant in the function. We can look at that tangent and see what kind of slope is it. Is it a positive slope, a negative slope, or is it remaining constant? This is a lot of information that we're getting from this mathematically. Now don't worry, if you haven't had calculus yet, we're not going to use calculus in this chapter or any part in the course. But I just wanted to relate something that you may have had leading up to this part of the chemistry so that you could see an application of the math in something different. All right, let's do an example. Again, no calculus needed. Let's take a look. For this reaction, it's going to run at 25 degrees Celsius, that's standard temperature. We're going to say that ammonia, which is the NH3 we see here on the right, is produced at a rate of 0.050 moles per liter per second. What are the rates at which nitrogen and hydrogen will be consumed or used up? All right, so you can kind of get a sense we're going to do some stoichiometry here. And what do I always say? You start with what's given. We're only given the rate of our product. That's all we have to go on. Let's go ahead and start there. So we're going to do two calculations here. We're going to do one for our first reactant, the nitrogen, and then we'll do a second one for our other reactant, the hydrogen. And so we're going to just put them side by side. So we're first going to start with the rate that was given for our product. And then what do you think we'll do next? If you guessed mole ratio, you're right. It's the only way we can go from one chemical to another using a chemical reaction. And so we're going to cancel out the moles of NH3 and now represent the value of our rate that was given initially in terms of our reactants. So we have nitrogen up here in this top calculation and hydrogen in the bottom. And you'll notice with these mole ratios, we have the 2 moles for NH3, that's from the balanced equation right here. And then we have 1 for our nitrogen because there's no coefficient in front, so it's an understood 1. And then the 3 here for hydrogen is coming from our balanced equation right there. Okay, so do we want moles of each chemical? Yeah, we're going to keep that. And what we're going to do is we're just going to cancel out this duplicated mole here, this duplicate mole that we would get in the denominator. That's going to cancel out here, but we still have one in the numerator. So there it is. And then the liters per second have no way to cancel, so they tag along. And so our unit here represents the unit for the rate that was given for ammonia. So with that check, there's a good chance we've set this up correctly because we have the same units for our rates of reactants. And so just doing the math, we get 0.025 moles per liter per second of nitrogen being used up. And we also get 0.075 moles per liter per second of our hydrogen being used up. Do you think these answers make sense looking at the balanced reaction? Yeah, they should, because with nitrogen, these are both diatomic molecules, right? So that's not a factor. But nitrogen is being used up half for each ammonia molecule, right? Because we have just one atom coming over to make a nitrogen molecule. But our hydrogens, we're using 3 hydrogens for every nitrogen molecule. So we're going to be using up the hydrogen much, much quicker. And so we see that with a greater rate value. All right, I really like this picture because it's just a graphical way to show you how a chemical reaction takes place. So a lot of folks, they initially think, oh, chemical reaction just happens like that. We go bang from reactants to products and that's it. No, they're a gradual process, and the time can be different. It can take very quick, right? Like snapping my fingers, but you're transitioning in that time period from all reactants to part reactant, part product to all product. And so each reaction is going to be a little different as to how fast that middle transition is. So this picture really slows it down and allows you to see graphically what's happening here. So let's look at our axes. We have time on the x in seconds, and on the y, we have number of molecules, and we can assume there's a times 10 to a certain power here, but for simplicity, we're just writing the front there. So 10, 20, and so on. All right, so the purple is representing our reactants. And so you'll see at time equals 0, we're at the top of the graph. We have a maximum number of molecules for this graph. Also at time equals 0, we have a 0 number of molecules for this green color. That's representing our products here. So let's see, as time goes by, we're going along the x-axis, we're getting more and more of our green product. As we go to the purple side, our reactants, as time goes on from time equals 0, we're getting less and less of our reactant. Reactants are being used up, products are being formed. We have an intersection here, and that's where we have equilibrium. Okay, so equilibrium is not saying that we have the same amount on each side necessarily. What it's saying is the formation of products and the formation of reactants are occurring at the same rate at this moment. So, chemical reactions are not always one way. Many different reactions, we'll see that in the next chapter, that many reactions will flip back and forth. Products break down, they reform the reactants. The reactants then form the product breaks down, we reform reactants again. And so that's more of where this point in the graph represents this. And so then we have this reaction continue on and make more product. So that's our green line. And if we follow this up at the top of the graph at any point on this green line, we see a picture representation of what's in that beaker. So we could see more green particles here than purple. If we follow this line straight down, we'll see that our purple has drastically decreased from where it started. So the picture just follows along with the graph. We're using up more and more of our reactant until we use it up completely. And if we follow that up to the top, there's no more purple in this beaker. It's all our green product. But we want to use stoichiometry, don't we, to be able to figure out these specific reactions. So let's take a look here. So it says in most reactions, the coefficients of the balanced equation are not all the same. You know that from Chem 1. So we have an example from earlier that we're bringing back here. We're forming that HI gas. And so we have hydrogen and iodine, and we could see that our product has 2 moles, and each of our reactants are just 1. So that's going to alter the rate for these different substances. So to be consistent, the change in the concentration of each substance is multiplied by 1 over its coefficient. Back up a second here. And so what do we have? We have the rate equals, notice the sign, negative, a general equation of A plus B yields C plus D. And so in this reaction, we're going to have our reactants with a negative in front. There we see them. And we have 1 over their coefficient, which is represented by this lowercase a. And then on the other side, we have equals, right? We have our pluses because our C and D in a general equation are products. And so you see 1 over the coefficient again, right here and here. Yes, there's a rate law. So the rate law is a direct proportional to the concentration of each reactant, and we're going to see it raised to a power. So let's take a look at this. We have a reaction, a decomposition, some substance A directly decomposing into a product. And so we can write a rate equation for that right here in the center. The rate would be equal to K, and then we see the concentration brackets are substance A and an nth power. Okay, so let's take a look at this general rate law. So in this rate law, the n, the exponent there, is called an order. And so it's usually a whole number. It's going to determine the rate dependence on the concentration. So how quickly or how slowly the reaction will take place based on how much of this particular material we have in the reaction. K is a rate constant, and so we'll see that a little later on. Notice that it says the concentrations of the products are not in this rate law, and that's because we're looking at a particular reaction, in this case, where the reverse reaction doesn't influence the rate overall. So this is not an equilibrium. We would see a double arrow that way, where it's pointing in either direction, meaning it's flipping back and forth. We don't see that here. This is a one-way reaction, and so we're not going to include products. All right, so the reaction order, that's that exponent. If we add up all of the exponents of a rate law, we'll get what's called the order for that reaction. So let's look at this example. In the rate law, rate equals K, concentration of nitrogen monoxide to the second order, times the concentration of oxygen in the first order. We would add 2 and 1 and say that this reaction is third order overall. And so we have different reaction orders. So let's take a look at these different ones, and then we'll take them in a little more detail. So if we have an exponent of 0, that means the reaction is at 0 order. And that means the rate is going to stay the same. So for example, if I double the concentration of A, the rate is going to stay at the same pace it was at when I had a simple, not doubling my concentration, just the regular initial concentration of A. Doubling it, tripling it, quadrupling it will not change the rate of that reaction. That's a 0 order. When a reaction's in first order, the rate is going to be directly proportional to the concentration. So if I double the concentration of A, my rate's going to double. They're going to always match. And if we have a second order reaction, the rate is going to be directly proportional to the square of the reactant concentration, which sounds really confusing. But in our example here, if we still double the concentration of our A, the rate will end up quadrupling. Okay, so perhaps that makes it a little more clear to see what's going on in second order. And that's all the orders we have: 0, first, and second. So here's some pictures of our A decomposing into products, and we can look at it as the concentration versus time. So a 0 order reaction, we can see a straight line because no matter what the concentration of A is along this y-axis, the rate doesn't change. It stays on course. That's our straight slope that we see there. The first order reaction, we could see that we have a little bit of curvature in our slope, and then second order, our concentration is making even more of an influence on our rate, and so we see a more pronounced curve, and we also see the concentration remaining up as well. Over here we can have the rate versus reactant concentration now. So we have the rate on the y-axis and our concentration down here on the x. And so if it's 0 order, the rate stays the same. It's a straight line. Okay. Then we could see the rate for first order, okay, and the rate for second order. All right, let's get into our example 2. For a particular reaction in which A decomposes into products, a doubling of the concentration of A caused the reaction rate to double. So what's the order of this reaction? If you guessed first order, you're correct because of that definition we looked at. First order reactions When you double something of the concentration, the reaction rate's going to double. So they're going to be directly related. All right, so how do we get this order number? Well, these have to come from experimental data, and you'll always be given the experimental data. You'll see what that looks like in just a minute. And so we use this method called the method of initial rates. And this is where we take data from experiments in a table form, and we look at the starting concentrations. And from those starting concentrations of different substances, we can compare and look at rates. The best way to do this is to just show you an example, really, then kind of talk through it. So let's look at example 3. This is going to be several steps, and so you'll see that this will go on for a few slides. All right, so the order of a reactant is the power to which the concentration of the reactant must be raised to produce the amount of product indicated by the reaction. And here's that general equation I mentioned earlier. This is used a lot in text just so the numbers aren't making extra confusion, right? So we have a substance A with a coefficient of lowercase a substance B with a coefficient of lowercase b. And so the lowercase just represent any number, okay? And we're just pairing them with the substance using the same letter, just for easily trackable through the work here. And so we're given the data table that you see down here. We ran this experiment 3 times. That's what the trials are. And so in the first experiment, we had a starting concentration of A of 0.02, and that's moles per liter. And our starting concentration of our B, our second reactant, was 0.01. Okay, then we'll look at the second experiment. Okay, looks like we doubled our concentration here of A, so we're starting at 0.04. And our B didn't change. We kept the concentration of B the same here for the second experiment. And then if we go to the third time we ran this experiment, we kept A the same now. It's still at that 0.04, but we changed our concentration of B to 0.02. So do you see any kind of pattern here? If we look at experiment trial 2 and 3, concentration A didn't change, but concentration B did. And then we have a rate change here between trials 2 and 3 as well. So if you're thinking that, hey, if those are the same concentration for those 2 experiments, that will not be a variable that we will have to consider, and we can calculate just B, you're onto something. Let's look at trials 1 and 2. And so looking at this, we see that the concentration of A was doubled, but B was unchanged. So we can use that fact that B was not changed in these 2 trials, but A was, to figure out A's influence on the rate. And so we're going to just look at those values that I've bracketed off there with those red arrows. Okay, now let's see what happened here. So we could say that A is doubled, right, from going from trial 1 to trial 2. Look at the concentration change. We went from 0.02 to 0.04. So our concentration of A has doubled. And then what happened to the rate in that same time? The rate was increased by a factor of 4. I know these are really small decimals, but if we ignore the non-significant zeros, see what I did there? In front, we would see that we have 12 and 3. 3 times 4 is 12. And so that's how we're getting a factor of 4 change for trials 1 and 2. So we're given 2 pieces of information. Our concentration is doubling, and our rate has just quadrupled. What order is that type? You see it in blue down there. It's second order. So A has to be second order for this reaction. We would use an exponent of 2. And so this is the math on how to figure that out. Again, we can talk through these numbers because they're so small and it's easy to see 2 going to 4 and 3 going to 12. But showing you the math here, I think will be helpful because not all the time are the numbers going to be nice and clean like that. And so you might have to do the calculation here in order to see exactly how the relationship is. Okay, so now it says we're going to look at concentration B. So you see that I've bracketed the two bottom concentrations for B and then the rates, and I've moved my highlighted portion down to those two reactions as well. All right, so let's look. We've doubled concentration B, and what happened to the rate? 12 to 24, that doubled as well. And so we've looked at the types of orders, and this is a first order reaction. Here's the math that we did if you want to pause it and take a look. All right, and so the conclusion for this is we had our data, and the rate law can be written as what you see here. K, again, we haven't talked about K yet, but it has to be present in the rate law. Concentration A to the second power, because we determined A was second order. And then you see there's no number here for B. Just like a coefficient, if there's no number there, it's understood to be 1. If you want to put the 1 there, go ahead. But if we don't see it, you'll know that it's understood to be 1. And so the overall reaction order is the sum. So we have 2 plus 1. This whole reaction is third order. All right, let's do a quick check to see if you get the idea. How do the exponents, which are the orders in rate laws, compare to the coefficients in a balanced equation? They have no relation to it. That's a typical mistake, though. Students will use that. They'll look at the coefficient in the balanced equation and automatically make that the order. And just keep in mind, there's no relation to how that works. Okay? So it has to be figured out the way we just looked at in that last example. All right, so integrated rate laws. So that's that integration that we talked about with a little bit of calculus influence there. And so this is going to show the relationship between rate and concentration. And it's useful to have an equation relating concentration with time. But using calculus, we can obtain the integrated rate law that shows the relationship between concentration A and the time of the reaction. Now, again, we're not using calculus in here. You're going to see an equation, okay, but we're always going to relate it to algebra as the slope-intercept form. And so you'll recognize that. So it's starting out with a calculus uh, look to it, and that's how these rate laws were derived through calculus, but then we're able to back them out and go into a more linear algebraic look. And so we'll stick with the algebra as far as math goes. Okay, so don't be scared if you haven't had calculus. So we have our rate law. Let's look at this example. So we'd say A to the first order, and so we would rewrite that cleanly as no exponent. It's understood to be there. The integrated rate law would be taking the natural log of our concentration and setting that equal to opposite our K constant times time, and then add the initial concentration of A, its natural log. And that looks like a huge mess. Okay, what we're going to look at here is the pattern of what the graph looks like. What are the axes on the graph for each type of order? And that's what you need to focus on to learn. So we have a rate. Okay, the rate is molarity per second. The K value that we're going to plug in for a constant for first order is going to have the unit of second inverse. And so that means 1 over second when you see the exponent like that, if you weren't aware. And for first order reactions, we're always going to see the natural log of A versus time. Those are our X and Y axes. Okay, so let's take a look at what this graph typically looks like. And again, each order is going to have its own look. And so we want to focus on this. A first order integrated rate law, we're going to plot our natural log. Our slope is going to be opposite of our constant K. And it's going to look just like this each time, a negative slope. So we can look at this example where we have this chemical, we take the natural log, we have some values here to compare. Our concentration, the natural log of it, is changing over time, and then we have our time here in seconds. And if we plot this, it has a negative slope. And so you'll also want to look at the axes. We have time on the x and natural log concentration on the y. Once you piece those three things together, the y-axis, the x, and the slope of the line, you'll know you have first order. And so that's what we're trying to show with these pictures. We're not going to be plotting any of these, but you'll see them and be asked to recognize them. So here's another example. Example 4. The reaction A forms B has been experimentally determined to be a second order. Okay, they're giving us this. The initial rate is 0.0100 moles per liter per second at an initial concentration of A of 0.100 moles per liter. What's the initial rate when the concentration of A is at 0.500 moles per liter? What? That's a lot, right? So we have this as a multiple choice question. Take a second, think it through. All right, and so here's what we look at for this. Since the reaction is second order, that was the most important piece that they gave us. We look at the concentration now, and we're going to see what happens. We're told the initial rate is 0.01, and the concentration was 0.1. So if you had to go back and make a chart showing that experimental trial, and if that makes it easier for you to see this problem, go ahead and do it. But we know that second order is causing our rate to quadruple. And so that rate would have to be the answer D here for our rate to quadruple. Okay. The first order integrated rate law. Okay, so we can write this in this way with the natural log. The 0 down here in the denominator, that means initial concentration. Instead of using an I like I've written, it's another notation. So it means the beginning. If we don't know the original concentration and we want to know how much reacted, we would use this formula. Let's take a look at this one in action. So a certain first order reaction has a rate constant of 0.25 1 over minute. How much time is required for this reaction to be 60% complete? So see how that's worded out? They gave us the rate constant here. This is the first time we're seeing something to plug in for that K. And now we're figuring out time. So let's go through how this would set up. So if it's 60% complete, we have to think of it based on 100. 60% is complete, that means we have 40% left to do. And so we're going to use that as our concentration ratio to plug in, not the 60 that they gave us. So we have to indirectly think, okay, if 60 is completed, 40% of that concentration remains. We have to use what remains to talk about this concentration. So that's why we're going to use 40%, which in a decimal is 0.40. And so we've plugged that into our formula here next to the natural log. Then we plug in our K, which was multiplied by time. We're solving for time, so we do some algebra, and we get 3.7 minutes. It's minutes because our rate constant was given as 1 over minute. And so after doing all the algebra, it flips that and becomes minute in the numerator. Okay, so what if we have a bunch of reactants? We have a really large reaction going on. What's going on? If we change each reactant, the overall rate's going to be affected by that. If we change the initial concentration of one reactant, the effect of each reactant's concentration can be determined. So this is going back and talking about the picture of the different trials, the 3 different experiments that we looked at. All right, so if you needed to go back, and I know this is really wordy, and just take a look back at that slide, do it, where we had the 3 trials of experiments and the data, right? So if we change the initial concentration of one, that effect of the rate can be determined because we'll look at the other substances not changing for those 2 experiments. That's what it's trying to say. And so here we have to give other letters to represent the order numbers because they're representing different numbers. And so now we're using a lowercase m for our order of our first concentration, our first reactant A, and we're just using the number n, the letter n, to represent a different number than the concentration for A. Okay, so that's all it's representing. So this is our resulting form. Okay, and again, our overall order would be adding up those exponents. All right, for second order reactions, the rate has the law written as you see it on the top here. If we were to integrate it, this is what we would do after that integration step. But that's not the important part to take from this slide. The important part to take from the slide is what does the graph look like for second order reactions? And that's where I've placed the star. The graph is going to be 1 over the concentration versus time. Okay, and so they say the slope is k, the y-intercept, they've given it there, and we use this form to determine the rate constant. We have our units of k down here. You should familiarize yourself with that as well for second order, what you should expect to see. Let's look at example 6 together right now. So we're told second order reaction. It took 112 seconds for 50% of the substance to decompose. If the initial concentration was 0.20 molarity, what's the rate constant? So we're trying to solve for K. And this is what we would have to do. So here we're going to say the time it took for half of the substance to decompose. If you're not familiar with that, that's called half-life. And that term half-life is usually set aside to talk about things that nuclear decay, so radioactive elements and things like that. But any substance that decays or forms a product, so its concentration is decreasing, and we're looking at the percent at which that concentration decreases, we could look at it in terms of half-life. So the T with the half subscript, that means half-life. Okay, we'll talk about half-life on another slide as well, so you'll see it again. But it's special here because of that 50%. It's half of the original material is left. So it took 112 seconds for half of that material to decompose. The initial concentration, which we see by that subscript 0 next to our concentration of this A, we're given as 0.2. We can solve for K. K is right here in the denominator. Second order reaction tells us to set it up as an inverse, 1 over the constant times the concentration initial. Okay, and so this just becomes algebra now. We plug in the time is in seconds. We keep the 1 there. That's our format for second order reaction. We have our constant that we're solving for, and our initial reaction has been plugged in. And so, moving things around, multiplying, dividing, adding, subtracting, and all that, algebra's out of the way. We end up with the rate constant equal to what you see up on the screen. So what does that picture look like? A second order rate law. Again, you want to focus on the axes. So this is the inverse of concentration. So we have 1 over the concentration of A along the y-axis, and then time is on the x. So if you picture a graph like this and you note the x and y axes, you see a straight line going up. Again, our initial concentration is some number value, so that's why we're not starting at the origin here. It is slightly up, representing that initial concentration has some kind of value greater than 0, greater than 0. Okay, we also have the 0 order. And so a 0 order reaction is when we have that constant rate throughout the entire reaction. So we can see that represented by the equation you see up there. So really, the concentration is not going to matter. And that's what we said earlier, right? So we can see in this reaction, we have the rate equal to the rate constant times the initial concentration, but it's a 0 order. And so the rate of our concentration doesn't matter. The rate of this law is actually just the value of our constant. Okay, that's why it's constant. Okay, so when integrated, we would get this format here. But what's the important thing? What does the graph look like for 0 order? And so we have the concentration versus time. And so we can see here that we have the concentration of our A, okay? The A sub 0, that's our initial. Oops, sorry about that. That's our initial. That's what that 0 means at that point. So we're starting at a very high concentration on this graph. It's very high up on the y. And then over time, we have that negative slope. But it's constant the whole time. If we were to do rise over run to check the slope of this line, you would see it's the same number as we go down and check that along this line. So it's a constant slope. Okay, yes, the K units are different depending on the order. Yes, you should familiarize yourself with the units of K for each type of order. So they're color coordinated here in this chart. You could print this out, you could rewrite it, you can stare at it. You can keep looking at the graphs is what I would suggest, so that you're constantly seeing the arrangement of the units and matching it to that order reaction type. All right, so here's the half-life. And so we do have an equation that we can use with a constant value that we can plug in up here related to half-lives. And so that's 0.693 is going to appear in most equations if we use that form. Another form is using the natural log and getting our half-life that way. And so the half-life is going to depend on the order, right? Because the order of the reaction is going to tell me how the concentration is changing over time. So I need to know that to know when I reach the half-life. And the half-life, again, is when I have half of my material remaining. So people think that the half-life is a period, is an amount of material, but that's kind of indirect. We're looking at the time. Half-life is a measurement of time, okay? And so it's the time when we're at 50% of our original amount. Okay, so pictures. I like pictures. Okay, here we are. Let's look at this picture. We have a first order reaction, so we have concentration versus time, and then our time period here. One half-life's time period for this substance is 100 seconds. What happens in that 100 seconds of time? We had our initial concentration here. It's given as 1.00. We follow our graph down, staying on that line. And at this point, we can go straight down and see our half-life time period, the 100 seconds, and then match it to the y-axis, and we're at half our concentration. It went from 1.0 to 0.50, half. So that half-life time period is 100 seconds. Okay, so every 100 seconds, this substance is going to have half of its material gone. Now, it doesn't just disappear. It'll either radioactively decay, okay, into different energies, which is a whole nother story, or it will turn into product, okay? So some other product. So we have another 100 seconds go by. Where are we at here? We follow our line over to concentration. We're at 0.25, or a quarter of our original concentration. So we've halved from 50, now we're at 0.25, okay? Another way to think about this is money. People love money. People are good at counting money because they love money. So if we had $1 and then we go down to 50 cents, we halved it. And then if I have 50 cents and now I have just 1/4, I've halved it. So if that kind of helps, you can use that. Okay. How many half-life time periods have gone by? Well, to get to this point where we are after 200 seconds, it's been 2 half-life periods. So a lot of terminology here, but if you just kind of take this graph apart little by little, you should be able to piece it all together. All right, let's look at each rate law. This is another good thing to take a screenshot of, print it out, or just rewrite it in some way so that you have it as like a reference. And so we look at this, we have the rate order listed, starting at 0 going down to 2. Okay, we have our rate law written out. The units that are constant will have. What the integrated rate law is, which you do not have to worry about learning, okay? Then what does the straight line plot look like? Again, focus on the x and y axes, right? Particularly the y is what's changing each time. And then what the half-life expression will be, you do not need to memorize that. Okay? So let's just take a summary so far. We're about 45 minutes in. So the reaction order and the rate law, they have to come from experimental data. We can't just calculate that out of nowhere. There has to be some experiment where we're given experiment one, we got these concentrations and this rate, and so on. Okay? The rate law relates the rate of the reaction to the concentration of the reactants. That's what the rate law does. The integrated rate law relates the concentration of the reactants to time. And you can see that from looking at the x and y axes. The definition of half-life is the time that it takes for a concentration to fall to half of what it originally was. The half-life of a first-order reaction is not dependent on the initial concentration. If you go back and look at the graph, you'll see. The half-lives of zero-order and second-order reactions do depend on those beginning concentrations. All right, so let's keep going. So if we talk about the graphs, all right, so we're gonna look at this graph here. We want to plot concentration of A and the natural log of A and 1 over. And so let's take a look at how this gets spread out. So whichever plot gives a straight line determines the order with respect to A. So if this is linear, when I have concentration versus time, then the rate law has to be zero order. If I plug in the values and I only get a linear graph when I have the natural log of concentration versus time, then that tells me it's a first order reaction. And if the first two options don't work and I don't get a straight line, but I try to plot the inverse of the concentration versus time, and then I get a straight line up here, then that confirms a second order reaction. So it's just another way to look at the graphs and a possible question that you could be asked, right? What would you expect to see in a graph for the different types of orders? Let's look at example 7. A decomposition reaction with a rate that is observed to slow down as the reaction proceeds has a half-life that depends on the initial concentration of the reactant. Which statement is most likely true for this reaction? Take a minute, pause the video, read through the options, think about it, and then come back. Okay, so what do you think? For a decomposition reaction, it slows down as the reaction goes, so our rate slows down. The half-life is dependent on the initial concentration. That narrows it down some, doesn't it? If the initial concentration does have a dependency on the half-life, then this has to be either zero or second order, right? And so the answer here is C. The best choice that would fit this scenario is if we had a doubling of the initial concentration resulted in the quadrupling of that rate. All right, let's look at temperature. And my goodness, look at this equation. We have an exponent that's a fraction and has all these variables in it. This is the Arrhenius equation. And so if we look at the rate law, the rate constant K is temperature dependent. So as we change temperature in the reaction, it's going to adjust our constant, which sounds like it wouldn't do that, but constants can change. Okay, so let's pick this apart. So here, I'm sorry for it being confusing, but this is the general format of the equation. That A, it is kind of an italic font here versus when we've seen A before where it meant concentration. Here, the A with the little e, that's representing this frequency factor. And you can see the definition there down the bottom. And then the e is an exponential factor, which includes the exponent. So it's e to that power, which is then the numerator of that power, the E little a, that stands for activation energy. And that's the minimum amount of energy we need to get that reaction to occur. So in the beginning, we talked about what we needed to have a reaction, right? And one of them was the amount of energy. So these two particles, If they just are in the same orientation and two have a reaction, but they just kind of bump together like that and then push away, there wasn't enough energy to break bonds and reform new ones. So we need a certain amount of energy, a threshold that we have to reach in order for that reaction to take place. That's the activation energy. And then we see R here as our gas constant, that 8.314 joules that we looked at in the last chapter. Okay, let's see, we can take the natural log of this equation, and yeah, it does look kind of messy, but we can then say that this now represents the equation of a straight line. We could say that the natural log of the constant here could be our y, and then we see an equal sign. Okay, we have two terms multiplied by each other. Yes, these are ugly looking fractions, but that could be like the slope of a straight line formula. And then we have a plus sign, we do down here as well. The natural log of a could be our y-intercept of a straight line. And so looking at this format, we can predict what the graph would have to look like in this equation and then what that slope would be equal to. All right, so another version of that linear form, a much more user-friendly version, is what you see up here. And so we see a familiar face here with the 1 over, but just take a note that we're using T1 in front of T2 for this equation, whereas in previous chapters we've had the second of our two measurements first. So I just want to point that out. And then also our rate constants. Notice that we have 2 above 1 here. And then we have our activation energy, which would be some value in joules, and our rate constant, which just gets plugged in as this value all the time. Here's an example of using that previous linear form of our Arrhenius equation in this. So we have chemists commonly use a rule of thumb that an increase of 10 Kelvin in temperature will double the rate of a reaction. What must the activation energy be for this statement to be true if the temperature increases from 25 to 35 degrees C? All right, now hold on. You gave me Kelvin, but now you're asking me to think about Celsius changing. And then you want me to give you activation energy? Okay. We're just going to take the information as it's given and plug it into the linear form. So what do we have here? We have a double rate. Let's make that the natural log of 2, since we had our k over here before, right? That's our rate. And then we're looking for activation energy, so that's going to remain a variable. We just follow the equation. The activation energy was over R. Here it is. And then that's being multiplied the 1 over temperatures. But here, we've got to convert these Celsius into Kelvin to use in this equation every time. So 25 degrees Celsius comes out to be 298 Kelvin. So that is first. That's our first temperature. Remember, T1 is first. And then we're going to subtract the T2, which would be 35 degrees converted into 308 K. And when we algebraically bim bam boom boom mixy mixy solve this, we get 53 kilojoules for the activation energy. So that tells us for this reaction that they're talking about, we need 53 kilojoules of energy for those reactions to hit and produce a reaction. Here's example 9. A reaction rate constant of 0.150 mole per liter per second at 25 degrees C. What's the rate constant at 50 degrees C if the activation energy is given as 35.0 kilojoules per mole? Okay, so now we're solving for the rate constant at an increased temperature, and we're given the activation energy to plug in for this example. Let's take a look. All right, it looks messy, but we just start with our original linear form of Arrhenius, and we start plugging in what's given, okay? So let's see, we're given the rate constant, that's my K, okay? I don't know what that other rate constant is. Whoops, sorry, I didn't mean to go to the next slide yet. Okay, so we're looking for that other rate constant, the K2. We have K1 up here. We were given the activation energy here. it needs to be converted into joules. You see that? That's because the R value, that gas constant, has joules as its unit. So if we have kilojoules, we need to convert that to joules first. Okay, lots of little things to remember, I know. And then we have our two temperatures here. Okay, so we simplify, and we simplify, and what we should get at the end of that, you could try it on your own, make sure you're typing it in the calculator correctly so that you get this answer too. 0.448 would be our X value, which would be our second rate constant for that other temperature. So this is a graph of activation energy. Maybe you've seen this before. It's just a very basic looking diagram. We're making water for this reaction. So we have the reactants at a very high energy. That's what makes them reactive. They're at a high energy. If chemicals are at a low energy, they're not reactive. And that's what they all strive to do. Now, we all know that atoms and molecules don't have a consciousness, so they don't have wants the way we describe them, but I'm using it as a way to help describe the natural tendency of things to form. Okay, so the energy of our reactants we see on this graph are very high. They have to still go higher to get to that activation energy threshold in order for the reaction to take place. This is hydrogen and oxygen here on the left. They can exist with each other in the same container and not react. You have to give them that extra energy, that push, in order to force the reaction to take place. And then you could see the energy drop as they've formed the very stable water molecules. Take a look at one other thing, though. Look at this arrow here for the equation. That's that double arrow that I've mentioned before. This is a reversible reaction. So you can also break water apart and reform hydrogen and oxygen gases. That's called electrolysis. We need to shock the water with electricity. One of the reasons why that warning's on your toaster, because look at all the energy we need to reach to go in the opposite direction for this reaction. Okay, two terms here. The activation energy I've already talked about, and then we have what's called an activated complex. And so this is like a hybrid of the reactants starting to react and connect with each other, but then they still have bonds that haven't connected. It's an intermediate. And so we call it an activated complex. It's very high energy because you see there, partial bonds. It's a hybrid. Okay, how does temperature affect the rate? So that frequency factor that we looked at on the Arrhenius equation is the number of times that the reactants get to that activation barrier per unit of time. Don't worry about that definition. It's kind of nitty-gritty. The exponential factor is the fraction of the approaches that are successful in getting over that energy barrier to make the products. Again, you're not going to have to know that definition for me. This is just helping you understand that equation and what the pieces are. And lastly, the exponential factor, as it increases, it's going to increase with increasing temperature, but that exponential factor will decrease if I increase the activation energy. So I'm making it harder, right? And I'm making it harder to reach the product side. All right, we're coming up on an hour. Here we are at example 10. There's not much more. Stay with me. Here we go. Which statement best explains why reaction rates generally increase with increasing temperature? Take a second, read through the choices, pause the video, come on back, we'll talk about it. All right, you've given it some thought, and the best choice here to explain why reaction rates generally increase with increasing temperature is choice A. The reaction rates increase with increasing temperature because, as temperature increases, there's a greater fraction of molecules that have enough energy to get over that activation energy amount. We call it a barrier because it's a amount value that they need to get over. All right, the last bit for this chapter is reaction mechanisms, and I honestly think these are kind of fun. So let's take a look at what it is. So we write a chemical equation to represent a reaction. All the reactions we've written before have been the overall, right? Hydrogen plus water, hydrogen plus oxygen yields water, right? But most reactions actually have a bunch of little steps to get to that final product. And so all of those steps together are called a reaction mechanism. And so we're going to take the rate law to help us understand this mechanism. So here's an example. We're given an overall reaction, you can see it there, and then we're told there are 2 steps to this reaction, and that's called our mechanism. And so the reactions in this mechanism are called elementary steps, so you'll see that term. And that means that you can't break them down any simpler. These are the way the molecules interact directly to form that overall reaction you see up at the top. Okay, these are the little steps, the little intermediate steps that get us there. Okay, now we're going to compare products to reactants here. Look at step 1. I have HI as a product. Okay, that's step 1. So I'm taking our reactants and I'm forming our products. That HI that was formed as a product is now going to be a reactant in step 2. That's the definition of an intermediate. It's formed and then it's used up. So you see how I've canceled out the HI because overall it's forming and then it disappears. It's not in the final product of the reaction. So it's not written in the overall reaction, but it does form. So we want to acknowledge that and show that. And we show it with the mechanisms. Okay, I've been talking for an hour. I'm not even going to try to pronounce that right now. But we have different ways that we can talk about the steps. So uni means 1, bi means 2, ter means 3. So we're just going to go with prefixes. Bear with me here. All right. Rate laws for the elementary steps. So because each step is like its own little reaction, they have their own activation energy. They're going to have their own rate law. And you might be going, my goodness, really? We're going there. Yes. So the rate law for an overall reaction has to be determined experimentally. But the rate law for each little mechanism step, you can deduce that from the step. Let's take a look at it. So again, we look at reactants, right, when we write a rate law. So for this first step, we have iodine chloride and hydrogen gas. So we could write the rate as the hydrogen concentration times the iodine chloride concentration, throw a rate constant in there, and there's no orders. Well, the order is 1. There's no coefficients, right, other than 1. And then for the next step, we can write that rate law, looking at just the reactants. Here we have the HI. It's there in that second reaction. And we have the iodine chloride again. So the rate would be the concentration of these 2 reactants for that step. Example 11, let's look at it. From the equations below that describe the 2 elementary steps of a process by which a certain chemical reaction occurs, write the rate law and the balanced chemical equation for the overall reaction. And so we're given 2 different things here. We're told that step 1 is a slow step, and then step 2 happens fast. Let's talk about what a slow step would mean and how that would relate to an overall rate. So the rate of something can't be faster than its slowest step. Think about that. So the slowest step is, the minimum to get the reaction going. And we see that happening here in step 1. We see the formation of products C and D. And so apparently that takes some time. A and B are completely consumed in that reaction. But then look at step 2. The C that we formed as a product in step 1 is now decomposing into new products, E and F, and that occurs fast. So let's take a look. The rate law is from the rate determining step. The overall reaction is going to be connected to the slowest step. So that's why it was important to say that here for this mechanism. So we're just going to focus on step 1 and say that the concentration of substance A and the concentration of substance B with our rate constant is going to be the rate law for the overall reaction. So I just shrunk the bottom and the top part of that equation and put it up there so we could reference it. So now to get the balanced chemical equation, we're going to look at the two steps and see if anything is made and then disappears. And we see that with chemical C. So because they're on opposite sides of the equation, it's a product, then a reactant, and it's used up, we can take it out of the equation, we can cancel it out, and then we get the last part there that we've kind of combined the two steps downward. The combination is our overall reaction. And so the intermediate here would be the chemical C. It forms and then it's used up. Okay, so this is a summary of the elementary steps, the types of reactions that they can be, the rate laws that we would determine from them, and then the molecularity of each of those steps. Just be kind of familiar with this. You don't need to memorize it. All right, example 12. I believe this is our last one, right? So let's knock this out. What's the rate law for the elementary step? Chlorine plus carbon monoxide yields chlorine, carbon monoxide, I'm not sure what that would be named, complex molecule. Okay, think about it, look at the choices that you're given, and then we'll go over it. All right, so if you picked choice D, you are correct. Okay, so none of these had the products there, which is good because the products are not represented in the rate law. So that's the first thing that we notice. Okay, the next thing we notice is the first two choices just had one of the reactants, but we need both of them. They both take part in this reaction. They're both going to contribute to the overall rate. What's wrong with C? There's our product, right? So that's not going to work. And so the elementary step is in the form A plus B yields products. If you go back to that table on the previous slide. So the rate law would just be what you see there. Whatever our rate constant is, if we were ever given that down the line for this problem, we could plug it in. And then our concentrations for A and B, this is second order overall, first order reaction for A, first order reaction for B. Okay, the rate determining step we can abbreviate as RDS. That's the slow step. And it's going to have the largest activation energy because it's the slowest. So it takes the longest to reach that barrier, to overcome that activation energy barrier, and get to the product side of that reaction. So they're showing a rate limiting section with an analogy with passing cars. I'm just going to skip over that. Okay, let's take a look at this reaction mechanism. So we have the overall written first, and then you see the steps 1 and 2 over on the left. So you want to be able to take a look at that and see that the overall reaction is not included as one of those steps. Okay, don't get them all mixed up because they look like they're all kind of thrown together. And then we're told that the first step is the slow step. Not always the case, but it's like most often. And then we have the second part of our reaction as the fast step. What else do we look for? We want to look at the first step, product side. Are there any products that are formed in step 1 that are now reactants in step 2 and not step 2 products? Can we cancel anything out? So you should be looking for these things. Okay, what if we have a two-step mechanism like the picture you see here, where we have a first activation energy and then a second activation energy to reach on our way to the overall product. So the first step here in this picture to reach that first activation energy, that must be our rate determining step. See how much taller the activation energy is? It's a greater value, so it's going to take more time to reach that. Okay, the last thing we're talking about here are catalysts. If you've had biology already, you've heard this term before. They increase the rate of a reaction. Okay, that's the bio definition. These are, in biology, they are enzymes, which are just protein molecules, and they help different components that need to react get to the same location and have that reaction. In chemistry, they're not a protein molecule. In chemistry, these are usually surfaces that a reaction will take place on, things that facilitate the movement of particles. These are usually rare earth metals like platinum, rhodium, things like that. They have good conductivity, so they can allow components to move around. The catalyst lowers the activation energy because it's that surface where molecules can come together more easily. And so if they can come together more easily and react quicker, it's speeding up the rate. That's the idea with the catalyst. So we have on the left a reaction of ozone forming molecular oxygen, and we're saying that process is very slow. Or we could have a catalyst with our ozone and add some chlorine, and that's going to help the reaction take place faster. So it's not always a surface. It can be another component, but two versions of a catalyst in chemistry terms right there. And it appears that's the end. All right. Thank you so much for hanging out with me for the last hour. I hope this was helpful. Take a look at your notes, and very soon you'll see homework number 7 for this chapter being posted up on Canvas. I'll see you later.